Yeah, graduation.
I was really lazy.
So,
Oh, I get it. First time I was, that's. Maybe it's the best. What do you do? This is the first time I played. So let's. Right. Okay. All right. We are approaching the end very quickly. We're reviewing tomorrow, as it says there, and then our exam is on Wednesday. It is not cumulative. I believe that the review activity is available in Brightspace if anyone wants to go ahead early. Excuse me, but we'll go through that tomorrow. I figured today would just take a couple of things that I came across that I think would be interesting to look at. These are not going to be assessed on the exam. If anyone has any questions from 7.2, 7.4, we can start there. Otherwise, I just like two topics in linear algebra that I think are cool. And then I also saved the Reddit thread a couple of years ago. There we go. Reddit thread a couple of years ago that I just thought was interesting. What is linear algebra used for? How did it start out? What's cool in math is some, and I might have mentioned this earlier in the semester, I'm not sure, but some things that start out as pure math is math just for the sake of doing like theory and proof formally and writing things down and coming up with definitions and all this. Like that's pure math, and then applied math is taking that theory and using it for different things. Oh, I think I did talk about it with the knot theory. There's a Veritasium video. Yeah, okay. There's a like sleep knot theory is something that's been studied for over 100 years, and it was not until the last like few that they came up with an application of it as it relates to like the things that they can come up with using knots, mathematical knots, of material that's stronger than Kevlar, which is cool. Kevlar is really strong. So that's the application, but from something that was just studied for the sake of studying math. Which yes, there are people that do that. But they're so cool. All right. So the beginning of this thread, I'm going to post a link to this thread in Brightspace because I'm not going to read all these words. But started out with to just give a bit of a history of linear algebra. According to Hazernix. But I think it's, I read through it and it sounds legit. But there was a cool one here. Here it is. How does today's world? So this one here. Well, I didn't like zooming in. There we go. Google became the world's standard search engine because in 2000 it produced better search results than any of its competitors like Alta Vista. Anybody ever heard of Alta Vista? Really? Oh, cool. Okay. All right. But by using linear algebra. Okay. And then the link here is a link to an article, I think, or just talking about the mathematics of a Google search. Okay. So that's cool. And then the second one, Amazon product recommendations. People who bought this also bought. How do they sift through millions of purchases and determine which products to put there? Linear algebra. And then the link there is, this one's to an article? No, yeah, this one's to an article about it. So again, if you're interested in that, cool. How does Netflix determine what to recommend to you? Oddly enough, Bob, linear algebra. By analyzing the kinds of movies you watch and then using linear algebra. So I mean, there's tons of other information on this thread, which is from r/math, which yes, I do subscribe to r/math because it's going on. Super interesting. So I will link some Brightspace for anyone that wants to read through it. It's purely just in case you're curious and like to read words. Hey, Grace loves it. She's totally gonna read this. I don't know. But it's interesting. I think you don't have to agree. I like it all. I like the left wrongs. Questions on that? Just read.
What is it? Did they use linear algebra for code breaking during World War II, or am I making?
Reading World War II, that would be like the Enigma machine with, what's his name? I only know this because I saw the movie, what? Alan Turing, yes. Was linear algebra involved in that? I don't know. Because that would have been early to mid 40s. Linear algebra has certainly been studied by them. I don't know the answer to that question, so that's a good, let me just,
I think
on this
I think
thread.
it's been used for code breaking at some point, but I can't remember for sure. if I'm making that up or not.
Of course, he doesn't go out in the code. No, and I'm sure the answer to your question is yes, in the broader sense of code breaking, I'm not sure about World War II. But super interesting. Okay, so for today, any other follow-up on it? The link will be in our space later at some point. For today, I wanted to cover two things that I think are interesting that you may or may not agree to go down the not to degree of difficulty, of course, but certainly again something I would test as well. Has anyone ever heard of the Fibonacci sequence?
No,
Yes.
that's not very important.
It's not very important. It's pretty cool. Oh, I'm not very that. Yes, we don't have to run it. There we go. Fibonacci sequence. What do you know about it?
That's one.
It's one. The second number,
One.
also one. Where did you first learn about Fibonacci? So high school course? Some nerdy high school teacher? Cool. High school or middle school? Okay, what's after 1 and 1?
It's one.
Which is usually 2.
Usually.
Next.
2 plus 1.
Next. 5, good.
8,
Okay.
13,
Keep going.
21,
Don't slow down.
34, 55.
You're done.
134. That? Yeah, I'm good.
It's eventually you can say it's done. All right. So the next two terms of the sequence are determined by the sum of the previous two terms. Right? The way that we write that is an plus 1, that's a subscript, is equal to an plus an minus 1. Okay, where the a subscripts, a1, a2, a3, a4, a5 are the terms of that sequence. In Calc 2, which you've all taken as Calc 2, this is called, do you remember what this is called for a sequence? Recursive definition, right? It's the definition of how to get the next term out of the previous term. Do you remember also in Calc 2, you have a formula for producing the nth term of a sequence by substituting into some an function, right? You see both in Calc 2, even if you don't remember, because time passes, right? You get your recursive definition of how to get the next term from the previous term, and you have the formula, I believe it's just called formula, of how to get the nth term by substituting n into the formula. So that's what we're going to investigate in this fun adventure in linear algebra, is how to produce a formula. Like, what if I didn't want to write down every term? What is the 57th term of the Fibonacci sequence? Why? Because I want to know. But I don't want to write down the first 56. Okay? And that was in linear algebra. So what we want to do is we're going to write an arbitrary vector of two Fibonacci numbers, an plus 1 and an. Okay, and then we're going to write out that is equivalent to, well, I'm going to break the top entry in that vector up into a sum of two entries. Like, how do I get the n plus 1 term? Well, I would get that by adding the nth term, an plus the previous one, an minus 1. Right? Okay with that? Get the next term by adding the two previous terms. And the bottom entry of that vector, an plus 0. Okay, so taking the top entry, broken it up into the some of the previous two terms. Bottom entry just says an equals an. Okay, so then we can take that vector and split it up into matrix times vector, an minus 1. Right? Yes. What are the entries of that matrix? Can you unmultiply?
2, 1.
Right? What goes here produces that row.
1,
1, 1. Yeah. The coefficients are 1 and 1. Right? So here or no, here, this 1 times an, 1 times an minus 1 spits that out. How about the next row? 1 and 0. 1 and 0, correct. Okay, excuse me. All right, so we're gonna call that 1110 matrix. We're gonna call that A, and then an minus 1. Okay, so going back to the beginning here, our arbitrary an plus 1 vector an is equal to capital A times an minus 1. Or I could do the same process to get, notice how I went from n plus 1 and n to n and n minus 1. I could split this vector apart again, do the exact same thing, and say that this is a times an minus 1, an minus 2, or a squared times an minus 1, an minus 2, right? The exact same processes up here would produce that idea. Okay, continue on forever. Well, not forever, but n times, and you would get a to the nth power times a, so that's 2 and a1, which is a to the nth power times 1. 1 and 1 being the first 2 entries, the first 2 terms of the Fibonacci sequence. Right? That makes sense? Questions? Okay, cool. How do you take a to the nth power and make it easy to calculate? Right. Yeah. Yeah, right, because I can take a to the nth power, that matrix up there, the green one, to the nth power times the vector 1, 1, and that spits out any Fibonacci number that I want. But a to the nth power is annoying to compute, unless it's diagonal. Okay. And so the rest of the process, now we'll move on to diagonalize A. We'll write that down. We're going to diagonalize our A matrix. So how do we do that? One, 0, and equals the inverse. I'm going to refrain from using my calculator for now. I may go to my calculator eventually. But how do I diagonalize? How do I get the eigenvalues first? I'm doing it by hand. Subtract lambda along the diagonal. Yep. So a minus lambda times the identity would give me, did I become a matrix correctly? Yes, I did. Would give me 1 minus lambda, 1, 1, and 0 minus lambda. And then we take the determinant, a minus lambda I. What was that? No, not that's just the determinant. And set it equal to 0. So our determinant being 1 minus lambda times negative lambda minus 1 equals 0. Okay, so let's expand out that algebra and then refactor it. Negative lambda times negative lambda is lambda squared. And then minus 1 lambda minus 1 equals 0. Factors? Damn it, it doesn't factor what you do. Calculator, okay, okay, so instead of x equals, it's lambda equals negative b is positive lambda plus or minus the square root of b squared is 1 minus 4 times 1 times minus 1 over 2, 1 plus or minus root 5 over 2. That unfamiliar to anybody? That's the common ratio, that's 5 feet. You feet 5? It's one plus or minus square root of 5 over 2. Well, actually, the positive root, 1 plus the square root of 5 over 2 is phi. And the negative root, 1 minus the square root of 5 over 2 is actually 1 minus phi. Which I'm gonna write for just condensing my work as much as possible. I'm gonna write it as phi bar. So our two eigenvalues are ugly irrational numbers, but I think it's kind of cool that we get phi like just by calculating the eigenvalues. Actually, do you know what, maybe Anthony does, so don't answer right away, Anthony, let everybody else have a second think. What phi has to do with the Fibonacci sequence? Again, you only know this if you've seen it somewhere before, you wouldn't just be able to pull this out of here somewhere.
Approximation to terms.
The ratio of two terms, yes, yeah. So if I take 2 divided by 1, that's not really phi. But if I take 34 divided by 21, that's kind of close to phi. If I take 134 divided by 89, that's an even better approximation of phi, et cetera, et cetera, et cetera. So why would I want the 57th wrong word, the 57th Fibonacci number? Because if I divide it by the 56th Fibonacci number, I get a really good approximation for phi. Okay, so the ratio of these two terms is the same as the eigenvalues of that matrix. Cool, that's neat. So then these are the diagonal entries of my D matrix. At least you write it as plus 1 minus. Cool. So now our next step, once we've got our eigenvalues, we're going to go ahead and find their corresponding eigenvectors. So for lambda equal to phi, we get, let's see, we're going to set up a minus b times the identity. X equals 0 in mixed raw operations. So what that looks like is 1 minus phi, 1, and 0 minus phi. Augment that with the column of zeros, and then use some row operations. Can I do this one without needing my calculator? I'm going to switch rows 1 and 2. 0. And then let's see. Use this one to eliminate that. Multiply it by negative parentheses 1 minus phi. This times negative parentheses 1 minus phi. I have the right boosts. But oh, actually, I have to expand down. This is 0, and then this entry with that calculation 1 minus phi times phi plus 1. But what matter that yeah, this that simplified. That is correct. Since I was wondering where the negative one, right? The row operation would be negative 1 minus phi times this. So then the negative and the negative cancel out. So I'm able to plus in here. Plus. So what does that equal? 1 minus phi times phi plus 1. Right? If we do this out, 1, distribute phi minus phi squared plus, oh, wait a minute, that seems familiar. Phi squared minus phi minus 1. Yeah, that says the same thing, except with a negative in front. So what's that equal? Same thing, 0. Technically that equals negative 0, but that's still 0. Okay, so this is 0, so we have a free variable is kind of the point. Good thing we do, this equals 0.
Don't we do that because we just have augmented zeros?
What's that?
Why did you go back to the?
Well, I didn't know what this simplified to. Until I pointed out here.
Okay.
Do you know that this equals 0?
Well, don't you know that just because you augmented it with zeros?
But what if this simplified to 1? Then do I have a free variable? Right, it has to simplify to 0 because I know that phi is an eigenvector, is an eigenvalue, excuse me. It has to be 0, but it is actually 0. And that matters, yeah. So that produces an eigenvector V1. That is, E at the top entry and 1 is the bottom entry, right? Because x2 is a free variable here, x2 is a free variable, and x1 is equal to phi times x2. So there's our first eigenvector. Questions? Sometimes this is fun, we're having fun. The next part, I'll just do a slightly bit more quickly for the other eigenvector. So we would take A minus B bar times the identity. Always x equals 0. That produces 1 minus B bar. 1 minus B bar. 0, 0. And I'm just going to write down what the corresponding eigenvector is without getting into the calculation. And it ends up being virtually the same, B bar 1. So if we're doing our A equals P, so that's a P, P inverse, the columns of P are phi1 and phi bar 1. The columns of D are phi0, 0, phi. And then the columns of P inverse, so maybe we can do that. What is P inverse? We'll write that over here. P inverse is equal to 1 over the determinant of P, right? We're using our inverse formula. And then, do I remember which to switch and which to negate? I don't know if I do. 2 of them switch to main diagonal switches, right?
I think that's right.
Yeah, I'm reasonably believe I think I have it on these steps.
Is there be a B bar and D?
Yes, thank you. Bottom line. Yeah, thank you. Okay, so we have 1 here, B here, and minus phi bar up there, and minus 1 there. Okay, we just need to determine the p, which I wrote p down right here, and then this goes here for our diagonalization. Determinant of p would be phi times 1 minus phi bar times 1. So if I want to simplify that, we have 1 plus the square root of 5 over 2 minus 1 minus the square root of 5 over 2. Which simplifies a little bit at least. The 1's cancel, 1 minus 1. The square roots of 5, there's 2 of them. 2 square roots of 5 divided by 2 is right on 5. Goes right there. So for our diagonalization, A equals PDP inverse. So this is times 1 over root 5 times 1 minus 1 minus phi bar and phi. Questions? Okay, so to go back to our arbitrary vector, our nth vector, that would be an plus 1, an is equal to a to the nth times the vector 1, 1, which is p d to the nth P inverse times the vector 1, 1. And plug in the things that we know. B1, B bar 1. B0, 0, B bar. Oop. And on those entries, to the nth power, times 1 over the square root of 5, times my P inverse matrix. 1 minus bar minus 1 B. Finally, times the vector 1, 1. That hot mess of a formula is how you can get the nth, the nth entry of the Fibonacci sequence. That's a horrible way to write it, so we should kind of condense all of that. Excuse me. And let's see. I'm not going to go through all of this part of the calculation, but if I take my 1 over the square root of 5 out in front first, like just pulling him all the way out here, it's constant. So no commutativity to worry about there. And if you multiply that matrix, that matrix, that matrix, and that vector, it simplifies to b to the n plus 1 minus b bar to the n plus 1 on top, and b to the n minus b bar to the n on the bottom. That is a bit too much to skip, but for the purposes of time, I am going to skip it. But you would take this matrix times that vector, right? Row, column, right at that. Then it's a vector, this matrix times that new vector. Then this matrix times that new vector. And that's what it simplifies to. And so the end of this part, the nth term of the Fibonacci sequence, 1 over the square root of 5 times phi to the nth power. I'm just writing down the bottom row of that matrix above. Phi to the n. So it involves the golden ratio to the nth power minus the conjugate of the golden ratio to the nth power, and then the 1 over the square root of 5 gets the square root of this. So there's one application to diagonalization related to Fibonacci's, the Fibonacci sequence, and going from a recurrence relation to a general formula, which this is way harder than any process you did in Calc 2, going from a recurrence relation to a general formula.
I guess in theory, we could extend the Fibonacci sequence into the negative direction. Right.
By doing something with this,
Yeah, just plugging negative stuff.
phi to the negative somehow, yeah, but I think the way that we define the recurrence relation is we have to have two starting points. Right, taking that,
You can start anywhere, right?
well, I guess, what would be the zeroth term of the Fibonacci sequence would be 1 minus 1 is 0 to go backwards, 0 minus 1 is -1, I don't know.
So you'd have like 1, 0, 1, 1, 2,
Mhm,
and going the other way,
mhm. -1,
-1, well, you'd have like 0, 1, -1,
Isn't it?
positive 2, 1.
But it depends, because it's like.
yeah, no, that's a good thought,
Yeah, that's.
You can fold up the idea of Fibonacci and the golden ratio is if you pick any two initial values, so it doesn't have to be 1 and 1 for Fibonacci, any two initial values, but follow the same rule, meaning add the previous two to get the next one, add the previous two to get the next one, you still approach the golden ratio, which is just kind of cool. It's not dependent on the 1 and the 1 choice at the beginning of the Fibonacci sequence. It's dependent on the rule of add the previous two to get the next one. So that's just a fun fact. Okay, any questions on that? No, all right, one more here. The square root of a matrix. Square root of a dimensions. Because why not? Right? If A equals P D P inverse. And B is equal to P times the square root of P times P inverse. Where the square root of D, because we don't have square roots defined yet, is what equals, is computed. Entry wise. Meaning each individual entry is square rooted. Then B squared is equal to, well, P radical D. P inverse times P radical D. P inverse, which in P inverse, we've seen this calculation before, square roots of D's, it equals PD, P inverse, which is A. Okay, so based on how we define the square root of something, if B squared is equal to A, then what is B called? It's called the square root of A. Right? That's how we define square roots. 9 is the square root of 81 because 9 squared equals 81. B is the square root of A because B squared equals A. Okay. So find the square root of this matrix. So we'll say let A equal 0, 4 minus 1, 5. 0, 4 minus 1 and 5. Find B, that is the square root of A. Each category, figure it out. It obviously involves a diagonalization of A to start off. Based on what I wrote before, it involves a diagonalization of A. Who would I just give you wrongly? I'll give you, we don't need normalized ones, I'll give you the unnormalized eigen vectors. V1, 4, 1, and V2, those are really the 0.707s. This one. The vector values of 1 and 4, corresponding eigenvectors 4, 1, 1, 1. So we got our P matrix, 4, 1, 1, 1. We got our D matrix, 1, 0, 0, 4. And our P inverse matrix, 1 over the determinant of P, 4 minus 1 is 3. times. Switch those two. Negate those two. So we've got A equals PDP inverse, so we define B. But B equal P square root of B, P inverse. Or 1, 1, 1. Square root of D 1, 0, 0, 2, well, P inverse. Times a third. 1, 4, that way, minus 1, minus 1. And if you simplify, excuse me, all of the matrix multiplication, I'm gonna keep my 1/3 out in front just because it keeps the numbers nicer. It simplifies to 2, 7, -1, and 4. And we could check, and maybe we will check if I have time to type it in, but this 1/3 times this matrix times 1/3 times the same matrix, so 1/9 times that squared should be the original matrix A, or else I don't know what I'm doing. Okay, so we should be able to check, so this is B. Check that B squared is equal to A. Let me type it in. So I'm gonna see is 1/3 times square bracket 2, comma 4, semicolon, -1, comma 7. Use that bracket. I'm not showing you this. But you can see, 1/3 times my matrix, just distribute the 1/3 in. Take that same answer and square it. 0, 4, 8, 1, 5. So B is the square root of A. But that's not the only square root of A. I made a choice.
We minus 2.
I made a choice when I wrote down D. There are 4 different square roots of A. Based on the choice that I made when I wrote down D. I agree with what Anthony said, that's
And 1.
accounts for 2 of them. So I could have written down D right here to be 1, 2, as I did, or 1, -2, or -1, 2, or -1, -2. Right, all of the square roots on those, the positive and negative square roots of those 2 entries, all the combinations of them would produce a B matrix such that B squared is equal to A. And that is how you find the square root of the matrix. What's awesome is you use the same process for computing A to the pi. Because why wouldn't you want a matrix to the pi-th power? But it's the same general idea. Diagonalize, take your D to the pi-th power. There you go. Because how are you going to multiply a matrix times itself? Pi times pi. It's not as easy as computing 1 to the pi-th power and 2 to the pi-th power. And then times P inverse. Questions? Yeah.
So it's impossible to take the square root of a matrix that is not diagonal.
It's possible to take the square root of a matrix that is not diagonalized. Taking the square root of a matrix in this way does require that it's diagonalized.
But isn't it possible?
I don't know the answer to your question. It's a good question. Can I diagonalize or can I take a square root of a non-diagonalized matrix? Because they are a process of finding a square root, like how we did other factorizations. That accounts for when a matrix is not diagonalizable. I don't think it's a question, but it's a good question. Any other questions I don't have to answer? In short, linear algebra is cool. You took a good class. I'm a great professor. Have a fantastic day. See you around. We'll be able to.
Fixed my class rate for class number 30.
Because.
Supposed to add 2 points.
Yeah, 2 points to Michael.
Yeah.
Yes, I will. Why? Let's do that.
But
Why did I do that? What you took?
because you missed what I wrote, and then you took up points because you claimed that I didn't answer, but I did.
Okay. Here we go. Alright, and don't forget about the homework, if you don't have it done, send me an email, I can extend it. Thank you very much. Everyone, take it right now.
Alright, thank you.
I understood.